Question 5, Part A. Experimental work at CERN has been described as recreating the conditions that occurred just after the Big Bang. Describe what scientists mean by the Big Bang theory and give one piece of evidence which supports the theory. So in describing the Big Bang theory, essentially we're saying the universe was initially in a hot, very dense state and then rapidly expanded. That is, the universe started from a single point, a singularity, and then rapidly expanded. That's the Big Bang. In terms of one supporting factor, there are many different supporting factors of the Big Bang theory. The most common of them being CMBR, cosmic microwave background radiation. Then you've got your abundance of your hydrogen and helium elements. We can look at the redshift of galaxies. And the redshift of galaxies basically tells us about the expansion of the galaxy, expansion of the universe rather. And part of that you could also include Olber's paradox. As in, if the sky is full of stars, why is it we can't see them all? Why is the sky dark? In part B of this question, we're told during a television program, the presenter states looking through a telescope at the night sky is like looking back in time. Use physics principles to comment on the statement. Right, so this is an open-ended question. In order to get 3 marks for an open-ended question, we're just looking for good understanding. Good understanding. Now, good understanding in this question would be you talking about the sentences, night sky, looking back in time. Well, when we're looking at objects which are very, very far away, we're looking at the light from that or those objects which was sent out from the objects a very long time ago. For example, it takes 8 minutes for the light to get from the sun to us. So when we look at the sun, we're not actually looking at the sun. We're looking at the sun 8 minutes ago. When we look at a star through a telescope, we're looking at an object very far away, and therefore we're looking at the light from that object a long time ago. So the word telescope there gives an indication is looking at faraway objects. We're looking at very distant objects. And our value for the speed of light is 3 times 10 to the 8 meters per second. Therefore, faraway objects, if it takes time for that light to get to us, that means we are effectively looking at the objects backwards in time. So look at very distant objects. That's the telescope side of things. Looking back at time is the light seen from the distant objects has taken a long time to travel. Therefore, when observed, the light is from a time ago, as opposed to being the light from the object as it is now. Question 6. A student carries out 2 experiments using different power supplies connected to a lamp of resistance 6 ohms. In the first experiment, the lamp is connected to a power supply of EMF 12 volts an internal resistance of 2 ohms as shown. We're asked to calculate the reading on the ammeter, the lost volts, and the output power of the lamp. So we have our equation for internal resistance. The equation on the relationship sheet is E equals V plus IR. We can expand that out and say E is equal to IR plus I little r, load and internal resistance, which then we can turn into IR plus R, meaning our value for current is going to be E divided by R plus R, in this case an EMF of 12 over 6 plus 2, giving us a value of 1.5 amperes. In terms of finding lost volts, we know what the value of the current is, that's 1.5 amperes. The lost volts is equal to the current multiplied by the internal resistance. So that's going to be 1.5 multiplied by 2, giving us a value of 3.0 volts. For the power, you could use any of the power equations, P equals I squared R, P equals V squared over R, or P equals IV. I'm going to use P equals I squared R. P is equal to I squared R, which is 1.5 all squared, multiplied by the resistance of the lamp, the load resistance, which is 6, which gives us a value of 13.5 watts. In part B, in a second experiment, the lamp is connected to a different power supply. Supply has the same EMF, but a different value for the internal resistance. We're told that the power output of the lamp is now greater. Assuming the resistance of the lamp has not changed, is the internal resistance of the new power supply less than, equal to, or greater than the internal resistance of the original supply? You're asked to justify your answer. It's not a must justify, but justification is going to give you additional mark. Now remember how we calculated our power before. Well, I used P is equal to I squared R. Now we're told that the load resistance is constant. That means that the value for our current must have increased. So I squared must have gone up because P has gone up. If I squared has gone up, that means the current has also gone up. Now, if the current has gone up, remember we calculated our current? I is equal to E over R plus R. Load resistance is the same. The EMF is the same. So the only way that our current could have gone up is if our internal resistance, R, has decreased. Question 7, we have a capacitive question. We're told the charging and discharging of a capacitor is investigated using the circuit shown. The power supply has an EMF of 12 volts and negligible internal resistance. The capacitor is initially uncharged. The switch is connected to A and the capacitor starts to charge. Sketch a graph showing how the voltage across the plates of the capacitor varies with time. Your graph should start from the moment the switch is connected to A until the capacitor is fully charged, and numerical values are only required on the voltage axis. Okay, so our standard charging graph for voltage against time for a capacitor is this shape. Starting at 0, here's time, here's voltage across the capacitor. We have to include the units. We don't need to include units of times because only numerical values are required on the voltage axis. The voltage of the capacitor, the maximum voltage, is the same as the supply, so that is 12. In part B, the capacitor is now discharged by moving to switch B. The graph of current against time as the capacitor discharges is shown. We're asked to calculate the value of resistance R. Now remember, for a charging or discharging capacitor, the maximum current occurs when we're just initially starting to charge or discharge and is determined by the EMF and the load resistance connected in the circuit. We're already told the EMF is 12 and we need to find R, and from the graph we can say our maximum current is 2 milliamperes. Watch out. That's times 10 to the negative 3. So that would be a very common mistake here, to forget that this is milliamperes or just not notice it from the graph. So our load value R is 12 divided by 2 times 10 to the negative 3, which gives you 6,000 ohms or 6 kilo ohms. In part C, the 220 microfarad capacitor is now replaced with one of a different value, and the new capacitor is fully charged by moving switch A, is then discharged by moving switch B, just like we had before. The graph of current against time as this capacitor discharges is shown. First of all, you're asked to explain why the value of the initial discharging current remains the same as in part B, and then asked how does the capacitance of this capacitor compare with that of the original one. Well, we can see that the initial discharging current is the same, which means, remember when we calculated the load resistance before, from I is equal to E over R. If the initial charging current is the same, that means the EMF hasn't changed. That's the same supply and same load. The value of the capacitor has no effect whatsoever on the charging current, the initial charging current that is, because the initial charging current only depends on the EMF of the source and the load resistance. However, we can see from the graph that the time taken for the capacitor to charge has decreased. So if the time has gone down, but the resistance remains constant, that means the value of the capacitor, the capacitance, must have decreased, because the time taken to charge or discharge a capacitor is dependent on the capacitance and the value of the load resistance. The load resistance is constant, therefore it must be the capacitance that's changed. Right, in question 8, we're asked to use band theory to explain how electrical conduction takes place in a pure semiconductor such as silicon. Your explanation should include the terms electrons, valence band, and conduction band. Well, let's remind ourselves of the band diagram for a semiconductor. We have the conduction band at the top, valence band underneath, and then our fill band. So in an intrinsic semiconductor, our band gap is small. Now, because our band gap is small, that means that we only need a little bit of energy in order for electrons to move from the valence band to the conduction band. So small band gap means that some electrons, now only some electrons have enough energy to transition from the valence band to the conduction band. Allowing conduction, because conduction can only happen if electrons are in the conduction band. So we've said electrons, we've said valence band, and we've said conduction band. Now that little bit of energy that is required to move an electron from the valence band to the conduction band most likely will come from thermal energy, just a small amount of thermal energy. Question 9, a technician is testing a new design of car battery. The battery has an EMF E and internal resistance R. In one test, the technician uses the battery in the following circuit, very well-known circuit. Readings from the voltmeter and ammeter are used to plot the following graph. Here's the graph expanded slightly. Use the information from the graph to determine the EMF of the car battery and calculate the internal resistance of the car battery. Okay, well, in order to find the EMF, we just need to extend our line back to the point where we're cutting the y-axis, because when the current is equal to 0, there's no lost volts, therefore all of the TPD is EMF. And if we extend this line backwards, we find that we hit our 12 volts. So EMF is equal to 12 volts. Please remember to include units. In terms of finding our internal resistance, we have two choices. We could either go down our equation route using E is equal to V plus IR, or possibly the simplest method is by using the gradient of the graph. So the gradient of the graph is equal to negative the internal resistance. So negative R is equal to M. Gradient M is equal to y2 minus y1 over x2 minus x1. Most common mistake made here is that people mix up between their x's and y's. So probably what would be a good idea would be to write down some coordinates. So I'm going to choose two coordinates, some nice easy numbers. So here's a nice easy point at 240 and 6. And I'm going to choose another easy point, this one here, at 80 and 110. So my 2 points are 80 and 10. So that's x1, y1. And then I'm going to go for 240 and 6. And that's my x2 and y2. Then I'll plug them in, and I get 6 minus 10 over 240, take away 80, giving a value of negative 0.025. And remember, that is equal to negative R. Therefore, R, our internal resistance, is 0.025 ohms. In part 3, the technician accidentally drops a metal spanner across the terminals of the battery. This causes a short circuit. Calculate the short circuit current. Okay, so the short circuit current can be found two ways. First of all, we could extend the graph forward until we hit our maximum current, but we can't really do that here because our scale doesn't go far enough. The other way is to say that the maximum current occurs when we have zero effective load resistance, and therefore we're only considering the internal resistance. So maximum current is equal to E over R, because normally current would be E is equal to E over R plus R, but we're getting rid of our load resistance. Now we've already determined our internal resistance from the previous question. Irrespective of whether you got that right or wrong, if you use it appropriately in this question, you'll get the full marks. So our value of E is 12. Our internal resistance is equal to 0.025, which gives us a value of our current, I, of 480 amperes, which is rather large. In part B, we're told in the second test, the technician connects the battery to a headlamp in parallel with the starter motor as shown. The technician notices the headlamp becomes dimmer when the ignition switch is closed and the starter motor operates. Explain why this happens. Right, well, the motor is a resistance, just like the lamp is a resistance. If we add a resistance in parallel, then the overall total resistance, RT, is going to decrease. Now, if the total resistance decreases, that means that the current is going to increase. If the current increases, that means that the loss volts, remember loss volts is equal to I multiplied by R, is going to increase as well. And because my EMF is equal to my TPD plus my loss volts, if the loss volts increases, then that means the TPD must decrease. So TPD is going to decrease. Remember, your TPD is going to be across my headlamp and the motor, and that means less voltage to the headlight. Hence, the headlight is dimmer. And that's us.